All right, congratulations. We are moving into the regular grade 9 textbook. And so one of the first units we are going to do together is chapter 5 on polynomials. And you've done a little bit of work with working with powers of what we call monomials. So now we're going to work into something called polynomials. So this first lesson is just an introductory lesson, lots of terminology, so make sure you pay attention to the terminology. And again, if you need to just stop the video and write some things down, that would be an excellent idea. Most of the things are highlighted within the package that I've given you. So how it's going to work now is you've got to complete the work within the package, and then there's exercises that follow, drill exercises that follow each little section there. The answers for all the drills are at the back, but the answers for the individual exercises aren't. So we're going to have to make sure that teachers having a look at those as you move along. So don't go too far without having us come over and check your work, okay? So let's get right into the lesson. We're now making a transition from into polynomial numbers. So the first question that we're asked here is if we talk about our model for modeling just numbers, like a number like 234, how could we model that using base 10 blocks? Now, if you remember, with base 10 blocks, 100 was 10 by 10. So this represents 100. So this would be 100, 200, right? And now how do I represent a 30? Well, that's a 10 block, right? And it's 1 by 10. So this would be 110, a second 10, and a third 10. And so I've got 230, and now for 4, I just take the ones. 1, 2, 3, and 4. Now, how do we make that shift now into something where we don't know the value of the base? In our number system, we work with what's called a base 10. What happens if we don't know the base? So this is something that's 1 unit by x units. So we say that's an x tile. It's got an area of x, whereas this one is 1 by 1, and it's got an area of 1. So this, which is x by x, would have an area of x times x, or x squared. So that's an x squared tile. Now, because we want to deal with both positive and negative numbers, we're going to let yellow tiles represent positives and red tiles represent negatives. Now, on the photocopies that we made for you, of course, yellow and red don't show up. So what you'll notice is the yellow tiles look a little lighter and the red tiles look darker. Okay, so the darker tiles will be negatives, the lighter tiles will be positives. All right, so I'm going to move this over. So we want to model some things. So how would I model this? Well, if you notice, I have an x squared and an x and then negative 3. So an x squared, this is my x squared tile. So there's 1x squared. Now to get an x is different, right? It's one of these tiles. So this would be my x. And then I want a negative 3. Now, if I want a negative 3, I'm not going to use a yellow tile because the yellow tile represents a positive. So I'm going to use the red tiles for a negative 3. 1, 2, and 3. So this would represent x squared plus x minus 3. All right, let's try the next one. How do I do a negative 2x squared? Well, I can't, x squareds are the big squares, right, because they're x by x. So I'm going to have to use the red tile here. So 2 of those, 1, 2, and then 3 negatives. Notice I don't have any x's in this case. I just have x squareds and a minus 3. Negative 2x squared and a minus 3. Try. The next one, I want a positive 2x squared. Well, that's going to be slightly different. I'm going to need 2 of the big square tiles. Right? So there's 2x squareds. And then I need a positive 3x. 2, 3. There we go. And lastly, now I need a negative 3x plus 3. Well, negative 3x. Well, this, remember, I'm not going to use the big square because that's an x squared. So I'm going to use this tile. That's an x tile, but I need 3 of those. 1, 2, 3. Okay, and positive 3. Oop, I've got to use the yellow tile. So, and again, when you're drawing those for me, make sure that you either just shade them in real quick or you leave them light. Okay? All right. Let's move on then. So some terminology for you. It says a polynomial, and let me just highlight that. A polynomial is one term or the sum of terms whose variables have a whole number of exponents. Ooh, that's a big phrase there. Here, let me put it a different way. When I look at the variables, every variable has what we call a whole number exponent. So no fractions. They're all 1, 2, 3, 4, 5, so on. Okay, and we can have one or more terms. Now, how are terms separated? Well, terms are separated by either a plus or a minus. Okay, so 3x squared minus 2x plus 5 is an example of a polynomial, right? So to model this polynomial, we use 3x squared tiles, right? Here's my x squareds. We used 2 negative x tiles, so this is negative 2x, and we used 5 1 tiles. Okay, so this polynomial really has 3 terms. Notice how they're separated. The first term would be 3x squared. The second term is negative 2x, and the last term is the 5. Okay, so terms are defined as being numbers, variables, or the product of a number and a variable. So a 3 is a number, so that can be a term. An x can be a term, or an x squared can be a term, or I can multiply those together and get a 3x squared, and that's another term. Okay, now remember, terms are separated always by plus or minus signs. Okay, now another fancy term. So we've got terms, we've got polynomials, right? Coefficient. Coefficients are simply numbers that are in front of the variables. So if I take a look at this polynomial right here, okay, the numbers in front of the variables, well, there's 2 of them. In front of the x squared is a 3, and in front of the x is a negative 2. So those are my coefficients. We wouldn't call 5 a coefficient. We instead call 5 a constant term because it doesn't have a variable related to it. All right, so let's take a look at this whole polynomial now. When I start off with that 3x squared, okay, it's the one that has the greatest exponent, and that's my degree. So we would say that this one has a degree of 2. Okay, now I realize that this has an exponent of 1, but we just leave that be. Okay, this term has a degree of 1, but you know what? For the whole polynomial, we just take the largest degree. We don't add them, we don't subtract them, we don't do anything, largest degree only. And then this last one, let's get that one shown up here. The term 5 is what we call a constant term. Now, why is it called constant? Well, since it doesn't have a variable part, it never changes. Okay, and a constant term always has a degree of 0. Now, watch out in your notes. There was a misprint in one of these constant terms. It says right beside it, a constant term has degree of 0, but then it says 2. That was a mistake. Constant terms always have a degree of 0. Okay, always, 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 always. Okay, so we can use any variable that we want with polynomials. So whether you have an n or a p or an x or a y, it really doesn't matter. Okay, a variable is just meant to take the place of something unknown quantity. Okay, so all of these here, these 2 polynomials, could be modeled using this model here. So those would be really equivalent. All right. Now, more terminology for you. Monomial, binomial, trinomial. Okay? Monomial, way back in the day, we used to have mono sound, which meant just one speaker working. Mono, one term. So 4a is a monomial. 6 is a monomial. Negative 2p squared is a monomial. Okay? Binomial, just like a bicycle, 2 wheels, right? 2 terms. So this is a binomial, 2c minus 5. 2m squared plus 3m is a binomial, 2 terms. Okay? And then lastly, trinomial, tricycle. Tricycle, 3 terms, right? 3 wheels, 3 terms. So 2h squared minus 6h plus 4 is a trinomial. Now anything beyond that, usually that's what students say. What happens if there's 4? Anything beyond that, we usually just say it's still a polynomial. Okay? We don't name them beyond that. So usually we write them in descending order. So if I look at this polynomial, 2k minus 4k squared plus 7, we would usually put the largest power first. So we would rewrite it and we'd make it look like this. Okay, negative 4k squared. Now why the negative? Well, remember, we're subtracting that 4k squared. So that minus doesn't stay where it is. It has to travel with the term behind it. So we make it a negative 4k squared. Since there was nothing in front of the 2k, we represent that with a plus 2k and then a plus 7. So we would say that is, since it's got 3 terms, it's a trinomial. Since the largest power is 2, it's got a degree of 2. Okay. Now, one other thing that we want you to know is that algebraic expressions that have variables in the denominator, such as 3 over n, or they include a square root, we don't consider those polynomials. We have other names for them. Okay. So we wouldn't classify those as polynomials. So when we're adding, subtracting, combining, we won't consider those polynomials. So which of these can be represented with the same algebra tiles? So again, if I was to start with that first one, I'd want 3x squared. So I'd want something that looks like this for a. And maybe I should label the fact that I'm doing a. There's my 3x squared, and let me label that as a so we know. Minus 5x's. Okay, I need minus 5. 1, 2, 3, 4, and then lastly 5. So there's my minus 5x squareds plus 6. Okay, 1, 2, 3, 4, 5, and lastly 6. Okay, so that's A. Now what about B? Well, right away I should be able to tell whether I can represent B with the same algebra tiles or not. So if I start with B, I'd need 5 negatives. Now notice here, that's not what I've got. So obviously, no, B can't be represented in the same way as A. But let's do B. Now we need negative 5. So that would be 5 of these. So this is what B would look like. Now notice I'm going to put those last, simply because we put the biggest degrees first. Plus 6R. Okay. Plus 6. Now notice, doesn't really matter what the variable is, whether it's an R or like in the first one where it's an X, it doesn't really matter, right? It's just a letter to represent something unknown. Then I need 5R squared, or sorry, 3R squared. So the beginning parts are the same, aren't they? But the end parts aren't. So now if I was to look at C, and let's take a look at C, negative 5m. Well, wait a second. This one's got negative 5, right? Negative 5x, but negative 5m would be the same thing. Let's just check. Plus 6. Well, there's plus 6. Positive 3m squared. Guess what? A and C are the same. So C is identical to A. All right. Let's see what else we have to try. So now we want to model each of those using the algae tiles. Now, when you're doing this, you're going to have to draw them. Okay. So, but I will continue to use the algae tiles. Negative 2x squared. Now, is this a monomial, binomial, or trinomial? Well, let's model it first. Negative 2x squared, I need 1, 2 negative x squared tiles, and that's all I need. Since there's only one type of tile, this would be a monomial. All right, let's try B. I need 2b squared, so I need 2 positive squared tiles. 1, 2. A minus b, so I need a minus negative tile, a negative variable tile, and then positive 4, so I need 4 positive integers. 1, 2, 3, and 4. All right, now how many different types of tiles did I use? Well, I used 3 different types of tiles, so that would be a trinomial. All right, and for C, I need 5a. Now, that's positive variable tile. So 1, 2, and again, the fact that it's an A or an X or a B, doesn't really matter. Let's try that again. 2, 3, 4, 5. Okay, and 3 negatives. 1. Now notice again how many different types of tiles am I using? Well, 2, so this would be a binomial. Okay. Third example. Which polynomial is represented here? Well, now they give us the tiles, so we just have to have a look at them. So let's start with A. Okay, when I look there, notice that there's 2 positive squared tiles, so I would write that as 2, and again, whatever variable I want to use. We usually use X, because that's what we're used to, but it doesn't have to be X. It can be any variable you want. Some of the exercises that tells you what variable to use. And then if I look, I have 8 negative variable tiles, so that would be negative 8x, and I have 2 positive 1 tiles. So that would be, the A would be 2x squared minus 8x plus 2. Okay? 3 different types of tiles, trinomial. Okay, for B, so let me do B in a slightly different color so that we know which one we're doing here. B I'll do in blue. So again, I start usually with, sorry about that, the largest tiles. So there's 2 positive variable square tiles, so I'm going to call it a 2x squared. There's 8 negatives variable tiles, so negative 8x, and 2 positives. So if you look, A and B are identical. Right? Again, another trinomial. We would say it has a degree of 2 because that's the largest power. Okay, let's try C. Now C doesn't have any square tiles, and it has 4 negative variable tiles, and then 6 positive unit tiles. So obviously A and B are similar, C is not. Okay? That brings us to the end. So good luck. Sorry, this one was a little long for you, but hopefully we got you off to a good start.